paper, and I want you to write something about the paper. And I will give you, I'll give you more detail probably on Friday, because I want to make sure that you have time to take a look at this. Or you want to do this over Thanksgiving, do it over Thanksgiving. If you haven't picked your, if you've already picked your paper. I'm still needing to find more papers, so I'm going to spend some time tomorrow looking for papers. Okay? So what I'm really interested in this unit, before you start, before you really get going on the paper, is get a sense of what this paper is all about. So you should, at the very least, read the introduction of the paper and find some logical sequence. What did the authors already know, okay, leading into this paper, and what was it they wanted to know from the group of experiments that they did? Okay, so I'm going to be asking you, what did the authors already know? Okay, what did they want to know further? And then I'm going to have you also write a little section about, and so what has this got to do with, what kind of information do you think you're going to draw on from the course? So what I did was this morning, and this was the article. Oh, the other thing I'm kind of curious, but I'll find out. It's amazing how much work takes place outside the United States, which is totally reasonable. This whole paper came from Japan. Okay. So here's what I did. I kind of read through the introduction and picked out points that I would want to talk about if I were to do this paper, okay? And it would start with, this says, number 1, your gut bacteria, if you don't eat a high-fat diet, the gut bacteria that you have when you eat a lean diet will break down fibers that you can't digest into short-chain fatty acids, okay, which are acetate, which you guys looked at, okay, 2 carbons, propionate, 3 carbons, and butyrate, 4 carbons, okay, and they did all of their work on acetate. Okay, so that's we said that. Gut bacteria break down dietary fibers to produce short-chain fatty acids. Okay, so there were two receptors that used to be called orphan receptors, and orphan receptors are usually G protein coupled receptors for whom the natural ligand has not yet been discovered. Okay, so we don't know what the ligand is. Or the ligand is known, but what that receptor is supposed to be doing is unknown. So this is a GR protein coupled receptor. Okay, 41 and G protein. I know it's coupled receptor 43. Are both orphan receptors. However, they discovered that they bind to short-chain fatty acids. Okay, so we know that. So now we're beginning to link the bacterial production of acetate to a particular receptor, so I like that link. Okay, and then it talks about the difference between GRP41 and GRP43. Okay, so GRP43 or 41 activates an alpha I protein. G43 couples to either G or GQ, or alpha I or alpha Q. Okay, Okay, so they've discovered that, well, GRP43 is made in adipose. Or on adipose. Okay, yeah, and if for mice that don't have GRP43, they tend to be obese. Okay, so here's what they want to know. So here's what they did know, and then you get down always, by the way. Look at the very last page, I always start looking at the very last paragraph of the introduction. For me, that's an excellent starting point for for if I want to know what is this paper all about. I skip all of them, never read the abstract, because it's way too terse and I have to think. And usually you don't want to think. So my first choice is go to the very last paragraph of the introduction because it tells you what they want to know. And sometimes the very first paragraph or the last paragraph of the introduction tells you what did they find. So the role, but we don't know. We know that GRP43 is found in adipose tissue, but we still don't know how it's involved in metabolic processes. So that's what they set out to do. And they present the true function of GRP43 in adipose tissue. Okay, so what I'm going to ask you to do for homework for this unit is to read through the introduction of your paper and tell me what do the authors know and what do they want to know further. And if you can explain why they want to know that, that would be very helpful. I'm thinking of, I don't want to make this hugely long, but I think what I might want you to do maybe, on the paper, just so you have it at your disposal, is get a sense of what this paper is all about. So when I'm reading a paper, I don't want to read the whole paper, I just want to get a sense of what is this paper all about. One of my clues is, this is what I do. I go to figure 1 and read what they found. GRP is abundantly expressed in WAT, which is white adipose tissue, as opposed to brown adipose tissue. Okay, so that kind of confirms what they already know. And like I said, figure 1 almost always confirms, yeah, we know this, but we want to know why is it. We want to know why GRP43 is in white adipose tissue. Okay, look at this. Look at this. This is figure 2. Isn't that ridiculous? Okay, and all they showed was if you knock out GRP43 in mice, they become obese. Okay, they also embedded in that experiment, in that set of experiments, is that they're proving that the acetate that binds to GRP43 is coming from the gut bacteria and nothing else. No, we don't make it, or the mice are not making the acetate. The gut bacteria are making the acetate. And I cannot imagine, wouldn't you like to do graduate work on mouse poop? Probably not. Okay, so then this is experiment 3. This is why I didn't choose these earlier experiments. They showed that, okay, if you put GRP back in those mice, but only let the GRP be expressed in adipose tissue, okay? No other tissue expresses GRP43, just the fat tissue. The mice become lean. Okay, so their conclusion was, well, it's just that GRP43 in adipocytes is what's important in keeping mice keeping mice lean. Okay, and then they begin to figure out why GRP43 suppresses insulin signaling in adipose tissue, but not in muscles. I think I told you that for liver. Look at that experiment. It's just a crazy experiment. Okay, and then here's the experiment that you did. Okay, you'll recognize most of these figures. This was the one that appeared on the test. And this is what you guys came up with. This is what they chose, and this is what their last figure was. This is what we discovered. And I think all of you had that. Right? So notice that what you did is really what the author, and you discovered what the authors discovered. So pretty cool. Okay, so their surprise was this, and this. And so they didn't know that either going into this study. So what appears sort of in a maroon color, that's what they discovered. They didn't know that previously. They had no way to think that the beta gamma subunit was activating PLC. And so anyway, so it might be a good way. What I also want is a sense of what is this paper going to be about. you are probably going to only do, if it was this paper, you would probably do less than a figure. I mean, probably less than a figure, clearly less than a figure, okay? So, I don't care if you've selected what figure you want to describe or not, I just want you to get a sense of what your paper's all about. And I get that sense by reading the captions on the figure. Okay? If I want to know more about how did they show that, then you can read. Then I just look at the experiments. I read this and look at the experiments. I hardly ever read the text. Okay? I will give you hints later about how to read the text so you can get the most out of. You don't have to spend hours and hours reading the text. Okay? But clue number 1, the last paragraph of the introduction is a really good place to start. Okay? That kind of gives you what they wanted to know, and then everything prior to that is what did they know leading up to what they want to know. Okay? So I'll have a written assignment so it's more concrete. So what I'm asking you for in this last unit is much more concrete. Okay? All right, so that's that. Okay, and now we have the fun of okay, now we get to do more crazy pathways. I'm not tired of them. Yeah, we got it. Okay, here's what we're going to look at. Is there a reason for you to divide? And the answer is yes. Okay. Is it safe for me to divide? The answer is no. So that's what we're going to be looking at. So in other words, I'm going to somewhat assume that CDK2 is probably active by now in the cell. Okay, we can assume that CDK may be active in the cell. So if we're going to have to stop the cell from cycling, we're going to have to stop CDK2 activity somehow. Okay? Probably the most important mechanism to stop the cell from cycling is to activate the tumor suppressor protein, which is a transcription factor, p53. So back in the could be the late 1980s or the early 1990s. I'm trying to think more in the early 1990s. It was the Time Protein of the Year. Not that Time always has a Protein of the Year. I think instead of having a Person of the Year, they had a Protein of the Year. And P53 was that protein. Okay? That's weird. What I want you to realize, I drew, it looks like this is one protein. P53 actually, in its functional state, is a tetramer, okay? It's always a tetramer, and I decided, and in my old notes, I'd drawn it kind of like this, and I thought, well, that's misleading. It is a transcription factor. So when I draw P53, you're going to be constantly thinking tetramer. Okay, 4 P53s, and they're all P53s. It's not like NF-kappa P, which is 2 different proteins that come together. This is 4 P53 proteins. When cancer gene therapy was really popular back in the late 90s, P53 was the most delivered gene to cancer cells. Okay, and that's kind of neat. Herpes simplex thymidine kinase was probably the second most popular gene. And I'll show you another target gene that was used in cancer gene therapy. Okay, so I want to start out with looking at the P53 and look at different things that activate. Okay, so you have P53 kind of present in your cells because that's going to be the thing that will initiate a stress response. Let's take a look at the response. I'm going to start out with the most obvious, and that's apoptosis. No, cell cycle arrest. Apoptosis is kind of a, well, if nothing else works. Okay. And I'm going to put right next to it senescence. What do you suppose the difference between cell cycle arrest and senescence is?
Senescence is like permanent cell cycle arrest.
Right. So senescence is the cell will never divide again. The cell will never divide again. And the cell cycle arrest means we're just going to temporarily lock the cell in G1 until whatever the stressor is has been resolved. Okay. Which of, and I always ask this, and then people still get the idea that senescence means the cell's going to commit apoptosis. What cells in your body are senescent? Yeah, your neurons are senescent. Your skeletal muscles are senescent. They're not going to divide again. Okay? Or at least your skeletal muscles are senescent. You might add some nuclei to your skeletal muscles, but the cell itself is not going to divide. Okay? So senescence does not mean that the cell is apoptotic. Okay? And so I want you to use your senescent cells to think about that. So I always think of all these things when people write down that the senescent cell is the same as an apoptotic cell. It always feel like, well, maybe in you. I know. Okay, so we would hope that if P53 is active, this will stabilize, keep the genome from undergoing big translocations or big breaks in chromosome structure. Okay, so we would love to see it develop some genomic stability. It will turn on DNA repair enzymes. Genes that code for DNA repair enzymes. That's kind of cool. Okay, and that leads to genomic stability too. Oh, it might, and this sounds kind of odd. Okay, it might turn on genes that promote cell survival. Okay, so we know that even if P53 is active, it might create a senescent state for the cell. It will never divide again, but it certainly doesn't mean, well, the cell's got to die. Sometimes there's a survival signal to say, well, let's see if we can resolve this problem before we commit apoptosis. Like, whoa, hey, hold on there. I know we're hypoxic right now, but maybe we can recover from that state. So that there's usually an initial, well, let's kind of give this a try before we commit to apoptosis. And then the other one is apoptosis. Okay, so those are things that P53 can do. So it activates genes with a huge variety of functions. We're only going to look at some of the genes that P53 activates, we certainly can. Partly because a lot of the proteins, genes that activate, we haven't talked about the proteins that are coded for. Okay, so let's take a look at things that activate P53, because P53 is normally in your cell in an inactive state, waiting for that stress. Let's start here. So when your telomeres reach a short state, or as we would say in molecular genetics, an uncapped state, that means it's probably not safe for your cells to continue to divide. So P53 becomes active and the cells enter a permanent state of senescence. And the cell continues to live just fine, but it will never divide again. Okay, what kind of response do you think nutrient oh, I forgot one that's not on my hand up here. What kind of response do you think nutrient deprivation would cause? And I swear I put my cells in nutrient deprivation all the time. Huh?
Cell cycle arrest.
I would go cell cycle arrest. Probably no need for senescence, because as soon as the nutrients, like I fed the cells yesterday, they went 6 days on eating off the same food. But they're pretty tough. Hypoxia. Okay, not enough oxygen would certainly be dangerous. DNA damage, like don't divide now. Yeah, you don't want to pass on mutant DNA.
Would hypoxia turn on cell cycle arrest and survival genes?
It probably would.
Is it safe when we're drawing this to maybe draw a little dotted line to what it might do?
Yeah, you could. But I think also common sense could, because you know, telomere erosion, your telomeres are never going to get longer again. So that's sort of a permanent state. Nutrient deprivation, well, yeah, we'll probably get over that one if somebody would feed us. It just seems like the cells screaming, would you feed me? Okay, I'm going to give you 2 others and don't worry about them. Sometimes too much oncogenic activity in a cell, like too much MYC, too much cell cycle signal, the cell just doesn't do well with that. Okay, so that's what I meant. We're not going to cover oncogenic stress. And if there just aren't enough ribosomes going around, oh, there's a shortage of ribosomes. They might be stalled on messenger RNA and they're not available to start protein synthesis. One other response I forgot to point out, because it's not in the particular figure I stole, but it's well documented, angiogenesis. So one way to get over the hypoxia problem is, well, let's just get some more blood vessels into the area so we can get more blood delivered to this particular tissue. So a lot of times if somebody is developing a plaque that's cutting off circulation, angiogenesis can create blood vessels to go around that plaque area. So I always wonder, so why would you want to give angiogenesis inhibitors to cancer cell patients, or to cancer patients? Okay, so that's the P53, the most abundant, it's probably the most critical protein involved in responding to, is it safe for me to divide? And the answer is no. P53 is probably involved in that, in executing that answer and stopping the cell from cycling. Over 50% of cancers have a mutant P53, okay, but probably most cancers have altered P53 activity. So once we've gotten through the P53 pathway, I want to talk about, well, if you don't have a mutant P53, you can still lose P53 activity, and here's how. In fact, you're going to tell me here's how. Okay, so you need a huge piece of paper. You were Micah, you would be doing it on 11 by 14 inch paper. I just reorganized my paper. I know, don't panic. It looks like that, but don't panic. Okay, so we're going to look at how P53 responds to DNA damage. Okay, so we're going to simulate DNA damage as the stress that gives the answer to, is it safe for me to divide, gives that answer, no, there's too much DNA damage, okay? But I just wanted you to understand that that P53 is going to be activated in response to a whole bunch of other stresses. Okay, so how are we going to do this? I think I'm going to divide my picture up into two. Yeah, and then we'll be redundant. I'm going to just divide my picture up into two things, and then we'll okay, so we're going to look at DNA damage. And most of the work here was done looking at single-stranded DNA breaks. Okay, so SS is single-stranded, DS is double-stranded breaks. Okay, which can be generated, actually, it can be generated by a lot of different things. Let's assume that we are going to induce DNA damage by like radiation therapy for cancer. Or we were looking at, in molecular genetics, topoisomerase inhibitors would cause single-stranded breaks in DNA or double-stranded breaks in DNA. So we're going to look at, let's just pretend radiation therapy in cancer. Okay, this starts with, there are a whole bunch of proteins that bind to the double-stranded breaks or the single-stranded breaks. So there's a lot of double-stranded, single-stranded break sensors, okay? But it's the job of the sensors to activate a protein called ATM. And ATM is going to phosphorylate, it's an autophosphorylation step, and then it can separate. Okay, so DNA damage, a bunch of proteins are binding to the breaks in the DNA. ATM binds to those proteins that say, oh, here's a DNA break. And ATM autophosphorylates and becomes active. Okay, I'll tell you what ATM stands for. And then see if you can guess how it's pronounced. I don't think I'll ever be able to. Okay, go for it, what do you think?
Is it from the bacteria?
Huh?
Is it from the bacteria?
No, ataxia, what do you think ataxia means? Have you heard of ataxia before? It refers to imbalance. So people with ataxia have a hard time knowing, kind of responding to where their body is. And okay, so this is part of the symptoms of people with a mutant protein. Okay. This is ataxia-telangiectasia mutant protein. So on my middle sabbatical, I worked, when I was working in the gene therapy lab, there was some guy working with gene therapy of the ataxia-telangiectasia mutant protein, and I bet it took me about 2 months to learn how to say it. Okay, so people who have, so it was discovered in people who had ataxia, lack of balance, which is controlled in the cerebellum, but they also had a high predisposition to cancer because they could not respond appropriately to DNA damage. Okay, so this is a protein kinase. Of course. It's either a protein kinase or a G protein or a ubiquitin ligase, but it's a protein kinase. And I'm going to cover 4 substrates. I'm trying to think of how I want to, I mean, I don't want to, I'm going to create a mess here. Okay. All right, we'll do the obvious one. Okay, P53 is one of the substrates. Okay, now think about that. Each member of the tetramer is going to be phosphorylated, so if you're really going to try to draw this as a tetramer, you got to put 4 phosphates on. P53 is not active in an unphosphorylated form, but it becomes active in the phosphorylated form. Okay. And it binds to DNA. Turn on a set of genes. Okay, and I wanted to list some of the genes that